How has Moore's Law over the last 2-3 decades changed the kinds of considerations you have to take on board when you design new systems, when you figure out what projects are feasible? What has stayed, what are still the limitations? What are things you can now do that you obviously couldn't do before?
I mean, I think of it as actually changing quite a bit in the last couple decades. So like the 2 decades ago to 1 decade ago, it was awesome because you just wait and 18 months later you get much faster hardware and you don't have to do anything. And then more recently, I feel like the general purpose CPU-based machines scaling has not been as good. Like the fabrication processes improvements are now taking 3 years instead of every 2 years. The architectural improvements in multi-core processors and so on are not giving you the same boost that we were getting 20 to 10 years ago. But I think at the same time we're seeing much more specialized computational devices like machine learning accelerators, TPUs, very ML-focused GPUs more recently, are making it so that we can actually get really high performance and good efficiency out of the more modern kinds of computations we want to run that are different than a twisty pile of C++ code trying to run Microsoft Office or something.
Yeah. I mean, it feels like the algorithms are following the hardware. Basically, what's happened is that at this point, arithmetic is very, very cheap, and moving data around is comparatively much more expensive.
Right.
So pretty much all of deep learning has taken off roughly because of that, because you can build it out of matrix multiplications that are, n cubed operations and n squared bytes of data communication, basically.
Well, I would say that the pivot to hardware oriented around that was an important transition, because before that we had CPUs and GPUs that were not, especially well suited for deep learning. And then, we started to build, say, TPUs at Google that were really just reduced precision linear algebra machines.
Yep.
And then once you have that, then you want to
you have to see the insight that seems like it's all about kind of identifying opportunity cost. Okay, this is something like Larry Page, I think, used to always say, our second biggest cost is taxes and our biggest cost is opportunity cost. And if he didn't say that, then I've been misquoting him for years. But basically, it's what is the opportunity that you have that you're missing out on? And in this case, I guess it was that, okay, you've got all of this chip area and you're putting a very small number of arithmetic units on it. Fill the thing up with arithmetic units, you could have orders of magnitude more arithmetic getting done. Now what else has to change? Okay, the algorithms and the data flow and everything else.
And by the way, the arithmetic can be really low precision, so then you can squeeze even more multiplier units in.
No, I want to follow up on what you said, that the algorithms have been following the hardware. If you imagine a counterfactual world where suppose that the cost of memory had declined more than arithmetic, or just invert the dynamic you saw over the last decade.
Okay, data flow is extremely cheap and arithmetic is not cheap.
What would AI look like today?
That's
You'd have a lot more lookups into very large memories.
Yes.
I think.
Yeah, I mean, I think it might look more like AI looked like 20 years ago, but in the opposite direction. I'm not sure. I guess I joined Google Brain in 2012. I'd left Google for a few years, happened to go back for lunch to visit my wife, and we happened to sit down next to Jeff and the early Google Brain team, and I thought, wow, that's a smart group of people doing something.
You should think about deep neural nets, because we're making some pretty good progress here.
That sounds fun. So okay, so I jumped back in.
I wooed him back. It was great.
To join Jeff. That was 2012. I seem to join Google every 12 years. I rejoined Google in 2000, 2012, and 2024. But
what's going to happen in 2036?
I don't know. I guess we shall see.
Well, what are the trade-offs that you're considering changing for future versions of TPU to integrate how you're thinking about algorithms differently?
I mean, I think one general trend is we're getting better at quantizing or you having much more reduced precision models.
Yeah.
We started with TPU v1. We weren't even quite sure we could quantize a model for serving with 8-bit integers, but we sort of had some early evidence that seemed like it might be possible. So we're like, great, let's build the whole chip around that. And then over time, I think you've seen people able to use much lower precision for training as well, but also the inference precision has gone. People are now using int4 or FP4, which sounded like if you said to someone like, we're going to use FP4 to like a supercomputing floating point person 20 years ago, they'd be like, what? That's crazy. We like 64 bits in our floats. Or even below that, some people are quantizing models to 2 bits or 1 bit. And I think that's a trend to definitely pay attention to.
Just like a 0 or 1?
Yeah, just a 0 or 1. And then you have like a sign bit for a group of bits or something.
It really has to be a co-design thing because, if the algorithm designer doesn't realize that he can get greatly improve the performance, the throughput with the lower precision, of course the algorithm designer is going to say, of course I don't want low precision. Like that introduces risk, and then it adds irritation. And then then if you ask the chip designer, what do you want to build? And then they'll ask the person who's writing the algorithms today, who's going to say, no, I don't like quantization. It's irritating. So you actually need to basically see the whole picture and figure out, oh, wait a minute, we can increase our throughput to cost ratio by a lot by quantizing.
Then you're like, yes, quantization is irritating, but your model is going to be 3 times faster, so you're going to have to deal.